So yeah, without further ado, we've got Arun Natarajan. He's an associate professor here at OSU. He got his PhD at Caltech in 2007, and then for the next 5 years, he worked at. He was a researcher at IBM T.J. Watson, doing radar and multi-wave types of research. And in 2012, he joined OSU. Very lucky to get him here. He joined our great devices group. It was already very strong, and now it's even stronger. And he's won all kinds of awards, including the DARPA Young Faculty Award, the NSF Career Award. Might be the only, I don't know of anybody else here who's won both of those. That's quite an accomplishment. And he's done a lot of work with industry. He's worked with the DoD on government contracts and basic research with NSF and lots of interesting applications. So today we get to hear about some of his newer work in wireless. So yeah, go ahead, Arun.
Thanks a lot, Alan. Thanks for the kind words. It's been fantastic to be part of OSU over the last 8 years, and really enjoyed interacting with students and building a teaching research program here. Thanks, Tina, also for all the organization and getting this off the ground. Really appreciate the effort. So today's talk, I'm going to be focused on describing some of the challenges that are emerging in RF and millimeter wave. And this is mostly focused from the perspective of interferer rejection. We do a number of other things in the research group as well, but I've sort of focused on this topic since I feel this is something that both is very important from the view of circuit design, but also provides interesting collaboration points for researchers in other areas. So just to reiterate the background that Alan said, I grew up in India, moved to Caltech for a PhD, spent some time at IBM Research, and I've been at Oregon State over the last 8 years. For those that have logged in from outside, Oregon State is located in Corvallis, and that's a screenshot of the beautiful city there. And on the right, you see the Tele Engineering Center where our labs are located. I have fond memories of the place. Someday, I think I'll get to go back there once this COVID pandemic has passed. And at Oregon State, the area of integrated electronics has been an area of emphasis for a long time. We have a number of very well-respected researchers and teachers in this area. And also we have broad coverage. So we have people working on sensor systems, analog, mid-signal sensor interfaces, RF wireless circuits, as well as communication systems. So this creates great opportunities for collaboration and as well as an opportunity to address problems holistically. And these are the students whose work I'll be presenting today. All of the work has been done by them, and it's been a real pleasure working with the current and former graduate students in the high-speed integrated circuits group. I'll mention some names as I go along when I'm presenting their work. And I'd also upfront like to acknowledge our collaborators from various industry organizations as well as other universities. And increasingly the work that we're doing is becoming more collaborative as the problems that we're trying to address become more ambitious. And I'd also like to thank Rudy and Schwartz for helping us test a lot of these ICs that I'll be presenting today. So I'll begin by talking about the challenges and the history of what was done very quickly, and then present some more recent research work. So this isn't coming as news to anyone that sorry, let me just move this off the screen. I don't know if that's being shared. Yeah. So this shouldn't come as news to anyone that the number of devices that are coming online is very rapidly increasing. But what is interesting is that most of these devices are non-PC, and Cisco forecasts that in a couple of years, 80% of traffic is going to come from non-PC devices. And interestingly, these non-PC devices very often connect wirelessly. So what is happening is that more devices are coming online, and these devices expect to be able to access data wirelessly. So this has imposed a lot of challenge in being able to provide connectivity to these devices. And historically, over the prior generations of wireless system design, uh, sorry, some stupid going on. Yeah. The way that we dealt with this was to provide licensed and unlicensed bands for wireless systems to operate. So Wi-Fi systems, for example, have historically operated in unlicensed bands, which allows everybody to build Wi-Fi devices and deploy Wi-Fi radios, whereas mobile has been deployed in licensed bands, and this is why we go through carriers like AT&T, Verizon, or Sprint, T-Mobile in order to access these networks. But what's we see is that the spectrum below 6 gigahertz, 7 gigahertz, the spectrum in that range is very attractive. We call that the beachfront spectrum because it has excellent propagation properties. But that spectrum has already been allocated for various applications. So firstly, that spectrum is scarce, and where we are able to allocate it, we do it in a fragmented fashion. So the number of bands that we allocate in these frequencies are reflective of the fact that there are established applications that cannot be disturbed. So we allocate thin slices, and this has to be coordinated on a global scale as well. So a band that's available in Europe may not be available in Asia. So these have to be coordinated, or the receiver or transmitter has to be able to work across geographies. And from a Wi-Fi perspective, the amount of unlicensed spectrum that's available has been low. The popularity of Wi-Fi has now led to efforts to expand the spectrum. So we have Wi-Fi 6 coming online with larger spectrum that is available. But overall, these bandwidths are still not very large. So how we have tried to address this usually is through spectrum reuse. What do we mean by that? We basically reuse the same spectrum among multiple users by creating small cells. And we use the spectrum in one cell and then reuse it again in another cell and make sure that each antenna over here doesn't radiate so much power that it interferes with users in the next cell. But these kind of cell-based deployments are ultimately also limited because now as the wireless evolves, we come up with more complex deployment scenarios. So we might have a big macro cell that is serving many users. And inside this macro cell, let's say we have femtocells deployed. And it might help in some case for load balancing for a user that is quite close to a macro cell base station to actually be served by the femtocell. So at this point, this user is seeing a lot of signal power from the macro cell and must communicate with the femtocell. On the other hand, we might have some situation where we have a closed femtocell. Imagine a hospital where they don't allow any user to get onto a network. So at that point, you might have some users that are being served by a macro cell far away, but now see a femtocell that they are not talking to pretty close to them. So these kind of near-far problems can result in a lot of interference in the user. And the more the number of devices are, as we saw in the previous slide, the more the interference. And the other way that we have tried to address this thin slicing of spectrum is by using carrier aggregation. So the concept is very simple. Basically, use wherever you can find it. So let's say there's a slice of spectrum free in a band. Let's allocate it to the same user. So we began with contiguous carrier aggregation in LTE, and we now have non-contiguous carrier aggregation both within a band and both now across bands as well. And this creates a problem for the receiver because historically the receivers have worked by, let's say, filtering a one band and making sure that any interference in the other band is rejected. But now this receiver must be able to accommodate signals coming in from multiple bands. And this creates receiver design challenges to be able to support a wide frequency range, a reconfigurable wide frequency range, and at the same time be able to reject interferers or undesired signals that may be in this band. There is, of course, a solution to all this, which is to expand the spectrum utilization. Instead of trying to stay below 6 gigahertz, go to even higher frequencies. So 28 gigahertz and 38 gigahertz have emerged as 5G frequencies of choice. They call it 5G NR, new radio standards. And what's really interesting to someone who did his PhD in 2007, and during my PhD, I demonstrated the first the first millimeter wave phased array transmitter in silicon. It's taken about 15 years for this technology to now arrive, and Apple, the iPhone 12 Pro Max actually has millimeter wave transceivers in it. So this technology is mainstream. Automotive radar has been mainstream for the last 5-6 years, where we have 77 gigahertz collision avoidance radar operating in vehicles. There are applications for point-to-point links, but the important thing here is if you go to millimeter wave, you get access to very large bandwidths that both enable high data rate and new imaging applications. So what is the challenge here? The challenge here is that if we consider the amount of signal from the transmitter that gets through to the receiver, that is inversely proportional to frequency. So the higher the frequency, the more path loss that we see. And given this extremely high path loss, what this then requires is for the transmitter to generate a whole lot of power so that the receiver gets at least the minimum it needs to be able to decode the data. And generating this high output power from the transmitter is challenging in silicon technologies. And why do we want to do silicon? Because implementing these transmitters and receivers in silicon technologies, which can leverage all the global investment that has gone in to build microprocessors and digital chips, we can then make these transceivers very cheap and then bring the cost down to the point where they can be included in commercial mass consumer devices. What's the solution here? The solution here is similar to what we do with a flashlight as opposed to a bulb. We have a certain number of watts. Instead of radiating it in all directions, we say that, okay, what we'll do is we'll focus in a particular direction, and this will shine more light or provide more signal to the receiver, and the receiver will be able to then demodulate the desired data. However, this creates, of course, a challenge, right? Because now, if I don't allow for some possibility of movement or of basically being able to steer this beam, I limit my link. My link can now only talk in one specific direction. So the solution to that is to build some beam steering. And we do that using what we call arrays. So we have this transmitter over here. There are signals incident on each of the transmitters in the array. And mathematically, you can conclude intuitively that signals will combine in this direction coherently. So they will add up. But in any other direction, what will happen is that the signals will not combine with the same delay. So they will not add up in time perfectly. They will not be aligned. So they will get canceled out. And if I wanted to steer the beam, I have to change the relative delay in each element. So what I can then do is I can create a situation where the wavefront is such that if I look in this direction, sure, this path has more of a delay, but it has less delay over here. This path has less delay over here, but more delay here. So the two are compensated out and I get signal combining coherently in a particular direction. So we want to build beam steering capabilities. And for this, we need this to be electronic, right, in order to make it flexible. So this is on the transmit side. On the receive side, what we see is that signals arrive at each element with different delays. And then what we can do is we can see that, okay, these two signals are delayed with respect to each other by some amount. And if I can introduce a compensating delay in the receiver, what I can then do is make sure that these signals that arrive from different angles get combined coherently over here to build up a larger signal. So this made sure that signals from this direction get combined coherently, whereas a signal from another direction, it doesn't see the right delay configuration for coherent combining. So what happens is that these signals are out of phase with respect to each other, so they don't combine coherently and they get attenuated. So what we therefore have again on the receive side is directional sensitivity. So we want to receive from a particular direction, and similar to the transmitter, we can now have a link where both the transmit and receive are spatially focused on each other. And by implementing steerability in these delays, we can then steer the angle of reception of the beam. There are some noise and efficiency improvements as well associated with this transmitter and receiver, which make it particularly exciting for use in silicon. I'll be happy to go over that if there are questions. I'm skipping past that, but I wanted to mention that those benefits do exist. People have known about arrays for a long time. So this is one of the early arrays implemented 80 years ago at 18 megahertz, had 6 elements, right? You can see the antenna array over here. And as technology improved and the frequencies of interest changed, we were able to implement higher and higher frequency arrays with a larger number of elements. And clearly, as these get integrated and built on wafer scale technologies, the cost and weight and drops, the performance improves. So this process has been going for a while. And what is interesting, and I bring this up, my talks, is to note that Gordon Moore actually in that seminal paper in 1965, where he's talking about Moore's law and how the number of transistors in microprocessors is going to double. He also predicts that given the fact that we are now making more and more transistors on a wafer, and each of these transistors has zero incremental cost, what will happen is that we can now build complex ICs that even accomplish things like phased array antennas or microwave arrays of microwave power sources. And he imagined that it would revolutionize radar, because at that time, beam steering and beamforming were used primarily in radar applications. But we see, of course, with 5G and beyond, that this has a communication application as well. And as I mentioned, work on the academic front in this area has been going on for the last 15 years, demonstrated some of the first phased array transmitters operating at millimeter wave, 24 gigahertz, 77 gigahertz, which is the automotive radar frequency. And other groups have also done work in this area. And then this work moved to industry as well, with more complex demonstrations from your traditional industry cellular hardware, cellular IC manufacturers. And what's effectively happened now is that phased array ICs in industry are maturing. People have demonstrated arrays with large number of elements. one of the challenges is how to interface all these ICs with antennas. This is a problem again that we're working on, but I'd be happy to share results offline if there is some interest. In this talk, I'll focus more on one of the challenges or what goes beyond with phased arrays. So if we look at the way that we've described phased arrays, there are multiple input, single output systems. So you have multiple antennas, for example, in the receiver, and all the signals combine to create one output. Now that's a little bit of a waste because I'm getting information from one particular direction and rejecting information from all other directions. What I would ideally like to do is build something that looks like a MIMO array, where I'm able to receive signals from multiple different directions at the same time. So I'm able to form multiple beams. While this is desirable, implementing such multi-beam arrays purely in analog domain is challenging. So the most efficient or flexible way, at least, to do it would be to uh, take the signal in each path, digitize it, and once we have digitized the signals in each path, in the digital domain, we basically combine them with different phase and amplitude weights in order to form multiple beams. So I could receive signals this way. So you can see that the advantage would be that there would be multiple beams opposed to a single beam in a phased array. But this comes at a trade-off. The issue is that I might have a jammer that is coming into all my elements. And in a traditional phased array, what would happen is that this jammer would be nulled out because I would form my beam in a direction away from the jammer. And so this jammer wouldn't appear on the ADC. But if I want to build a digital beamforming array, what happens is that this jammer appears at every element of the ADC, which in turn creates a problem because now my ADC has to have a high dynamic range. And this is a challenge in terms of power consumption and has held back a widespread deployment of digital beamformers. So we believe that in general, where phased arrays are moving are from multiple element single beam output arrays to multiple element multiple beam output arrays, and we want to address challenges related to these kind of jammers or interferers in such arrays. And we can change the way that we think about these arrays by saying the following, which is that what we usually have is a situation where we have a lot of desired signals and maybe a few interferers. And what we would like to do is somehow synthesize an array in which we are canceling the interferer signal alone and receiving signals from all directions. So you can imagine that hypothetically this architecture where I have a receiver and then I have a subtractor which has isolated the interferer and I subtract it from every element, that will give me at every element a pattern like this, which basically provides a wide field of view and rejection of an interferer. And of course, in order to extend it to be more flexible, what I would like to do is have multiple interferers isolated so that I can subtract them out from my overall received signal at every element. So this is the field of view of the virtual field of view for every element. It's basically all the other directions except the direction of the interferer. Now to implement this, we need to come up with new architectures for receivers. And one of the concepts that we've been working on at Oregon State has been on generalizing the concept of N-path filters. So what are N-path filters? So N-path filters are switching circuits where you have to imagine that there is a switch terminated in a capacitor, and this switch is driven by these kind of LO signals, which we call non-overlapping pulses. And these pulses have a periodicity of T naught, And we have multiple phases effectively of these pulses driving switches that are connected to capacitors that are placed in parallel. And what can be shown is that if we ensure no overlap between the phases of these clocks, and then we look at the effective voltages that we receive on the capacitor, what we then see is this concept of reconfigurable filtering, where we find that the response, the voltage response that we see at this node, which is over here, what we see is that it's firstly selective, right? So we are getting some frequency domain filtering, and its center frequency is set by the periodicity of these pulses. Now, given our experience with digital signal generation, and since these are 0, 1 pulses, we know very well how to create uh, variable frequency or variable periodicity in these pulses. So we are now having a filter that is tuned by F naught. And where F naught is 1 over T naught, or the time period of these pulses. And what we can show is that the response of these filters looks effectively like a parallel LC network. This filter clearly looks like a band stop filter, but we can, by implementing these switches and capacitors in series, then show that we can implement a band stop filter. In this case, if we look at the waveform at frequency response at VL, what we will see is that it takes out certain frequencies, and those frequencies are set by the periodicity of these pulses. So we have now an approach where we can build reconfigurable filters in order to reject certain interferers or receive certain desired signals. What our contribution in this space has been is to recognize that what we are actually interested in is this vast, what we call the electrospace of signals. So if we think about a signal, it has some properties. It's coming from a certain direction, it's coming at a certain time, it has a certain carrier frequency, it might be modulated with a certain code, it might have a certain polarization. So there are these electrospace properties of signals by which we can distinguish signals. And what we want is a reconfigurable way to select and reject signals based on their properties in these across this space. So very trivially, by turning off my receiver at some time, I might be able to reject a signal that is arriving at the wrong time. So, but frequency, space, code, polarization present more complex scenarios of circuit implementation. And our observation was that if we drive the switches with certain sequences, what we can then show is that the voltage stored on the capacitor is the correlation of the sequence W naught and the input signal. And since that is true, what we can basically think of this NPath mixer as an array of correlators, a bank of correlators, which is correlating the input signal with certain sequences. Now we have to provide some properties for these sequences. We have to make sure that these sequences are orthogonal to each other. But provided we do that, what we can do is then start implementing interesting properties. So one such property is shown here, where I'm providing two sequences to two of these filters in series. And this work was by Abhishek Agrawal, who did a PhD in our group and is now at Intel Labs. And what he observed was that, okay, I can now start putting these NPath filters in series and drive them with different sequences. And by, let's say one sequence is a time periodicity of T1, the other one has a time periodicity of T2, then I can basically start building filters with two notches as opposed to just one notch. And I can independently tune both these notches by changing the period of this waveform. And this is a simple example of one kind of correlator that is running in such an N-path filter. But and another approach that generalizes this is this still further is shown here. So imagine that you have a system where the TX and RX are communicating with each other through what we call code modulated signals. So this is traditionally done. You might have heard of CDMA, code domain multiple access, in which signals are separated from each other by multiplying the signals with orthogonal codes. So traditionally, the way that a receiver works for such code domain processing is that we build our traditional receiver, we digitize our waveform, and then once the signal is in the digital domain, we multiply it with the appropriate code to recover the signal. But the challenge is that if there are strong interferers, both the receiver and the ADC have been pushed into nonlinearities. So the signal has already been corrupted by the time we are trying to multiply it with the desired code. And it would be interesting if we could find a way to multiply the signal with the code right at the front end so that we could reject it at the antenna. And based on the observation that these can be viewed as an array of correlators, we can do that. So in this case, what we would do is we would make sure that the sequence that's multiplying each of these mixers is multiplied with the code, the desired code. And when we do that, what we find is that say that this is our desired split spectrum code modulated signal. This is the interferer. Once we multiply it by the right code in this correlator band, what we get is that the interferer is spread due to the yellow and the desired signal is integrated. So it becomes stronger, right? The blue signal becomes stronger than the black signal. So this presents a way to do code domain filtering. And shown here is an example of that where we show that we can receive two code modulated signals simultaneously by multiplying them in each of these correlator bands. And so one correlator band is configured to receive PN1, the other correlator band is configured to receive PN2. And I should also note that these two code modulated signals, we show them to be at the same carrier frequency to demonstrate operation, but they can be at different carrier frequencies. All we would need to do is change T1 and T2. So we can at the same time provide reconfigurable code domain and frequency domain filtering. Given these capabilities, we then looked at extending this to the spatial domain. And in this case, what we implemented was a 4-element receive array and operating from 300 megahertz to 1.4 gigahertz. So the center frequency can be set by the periodicity of the LO. And by changing the phase of the LO between different elements, what we can then show is that we can receive signals from a specific direction at a specific frequency. So this here is a measured performance, which shows the pattern of each element of each receiver. And what we see is that there are two notches in the pattern. There's two notches in the field of view. One notch is at 500 megahertz, 30 degrees. The other notch is at 700 megahertz, 0 degrees. So the way that we are then creating this is a receiver that can receive signals from all directions and frequencies in that 0.3 to 1.4 gigahertz range. But certain frequency and angle combinations are nulled out, which is reconfigurable by changing the relative phase and the frequency of the sequences that we multiply in the N-path filter. So this kind of correlator-based approach demonstrates the first time spatial reconfigurable nulling for multiple interferers using a reconfigurable N-path filter. And this shows a practical demonstration of the use of this. Let's say that we have a blocker that is right in the desired band. So this is a weak desired signal. This is a strong blocker signal. and they are both incident on the array. And before the cancellation is or the filtering is implemented, there is no data that can be received. But once we implement the spatial filter, what we see is that we're able to notch out the blocker and get the desired signal demodulated. We demonstrated this at RF frequencies, but there is interest, of course, in building these kind of spatial nulling or cancellation architectures at even higher frequencies. So this shows just a very quick highlight of a 10 gigahertz implementation of a 4-element array. Again, the broad philosophy is the same, which is that detect the interferer, go back and cancel it from every element. So shown here, for example, are patterns for every element where we see these notches. So the important thing to remember is that now each of the receivers is looking at a wide field of view. So I can form beams in all the other directions. And any interferer coming from this direction is notched out. Again, example shown here of a blocker that is exactly on top of the desired signal. Both of them are incident on the receiver. And before the canceller turns on, there is random noise because the blocker is completely interfering with the receiver. But once we cancel it, we're able to get the desired signal back. I'll now switch gears and go even to higher frequencies, which require some change in architectures. But again, the objective is the same. We want to go from phased arrays to MIMO arrays. But if we look at the way, for example, phones are deploying these millimeter wave transceivers, let's say, for example, they have a couple of transceivers. The millimeter wave front end, or the part that processes the 28 gigahertz signals, is physically far from the modem, and the signals are routed from the millimeter wave front end to the modem. And as you can imagine, the real estate on any of these portable devices is very, very tight. And there was prior work in simplifying this interface where I want to send all the control and data between the modem and the front end over a single wire, over a single coaxial interface. But this work was done for a phased array. Now in a MIMO array, let's imagine that I have a 16-element MIMO array, then I'd have 16 data streams that needed to go back and forth between the modem and the millimeter wave front end, which creates a challenge. And we've been looking at that challenge. And one of the solutions that we've recently come up with is this concept of what we call a beam space receiver. So the idea is that we implement two features at the same time. We have a 4-element receiver here. And what we are able to do through our spatial combining and filtering approach is to take signals from multiple directions. So, and we form the beams, but not just forming the beams, we also then place the beams at 4 different IF frequencies and then interface this to the backend. So this way we are preserving the full field of view, and at the same time we are providing MIMO signal output, but there is a single wire that is now connecting the front end IC with the back end modem. So this kind of approach simplifies the IF interface. It simplifies one of the critical packaging challenges that comes up in millimeter wave frequencies. So this is the IC that Robin Garg led. A number of students were involved in this IC. And this has a 4-element 28 gigahertz phased receiver, but it has 4 outputs, and those outputs are put to 4 different IF frequencies. These are the PCBs and antennas. So we went all the way to antenna interfacing into antennas to enable over-the-air signal testing. So we can again show, for example, that if there is a blocker in an undesired direction, then we can form the beam in such a way that we can reject the blocker and still get our desired signal. On the other hand, if both beams are desired, then our receiver can then form beams at two different IF frequencies, one beam looking in this direction, one beam looking in the other, looking at this angle of incidence, and be able to concurrently receive signals at the same time. So what we are now showing is a path towards MIMO signals at millimeter wave that also provides some interferer filtering capabilities. In the final section of this talk, I'm going to show some work we are doing at low power in this space. So in very low power receivers, what we usually try to do is build an event-driven wake-up receiver, which when the event occurs, goes and wakes up the primary transceiver. This is because this wake-up receiver has to be on all the time, which is a drain on the battery. And if it was a primary receiver that was on all the time, that wouldn't work. That would drain the battery out too quickly. So we have a very, very low power wake-up receiver that is not as sensitive as the primary receiver, but still does a good job trying to recover just the wake-up sequence or the event that it's supposed to detect to enable wake-up. And traditionally, there have been a number of approaches to implement these low power wake-up receivers. Energy detection is a popular approach, where the idea is that I just demodulate the signal by detecting whether there is power or there is no power. So one is there is power, zero, there was no signal power. But when I do that, the problem is that if there is an interferer, I'm going to get signal power at all the time, and I'm going to miss my detection. And people have tried to solve this by placing a high Q filter up front. But this then creates a challenge because I don't have the ability to receive a lot of frequencies at the same time. If I try to improve my linearity and sensitivity by going to mixer first receivers, this again requires high Q filtering, which again prevents wideband operation. And what we have tried to do is address this challenge, because if we want to operate across multiple regions, we want our IoT devices to operate across multiple regions, multiple ISM bands, then we need them to support carrier frequencies going from 750 meg to 1 gig. And in order to support that, we cannot have this high Q interface between the antenna and the wake-up receiver. And we have an architecture based on these kind of end-path switching circuits, and we have a noise canceling approach that simultaneously improves the sensitivity of the receiver, while at the same time, because it's end-path, now I can move the center frequency by changing the clock. So this is the whole implementation. Obviously, I won't get into it because of a lack of time. So this work will be presented in ISSCC 2021. But we have a number of concepts here that include end-path reception up front, and end-path filtering and code domain filtering in the back end to provide interferer rejection. And shown here is that even while consuming only 170 microwatts in the wake-up receiver mode, the proposed receiver achieves excellent sensitivity across the entire band, as well as signal to interference ratio. So this dot, for example, means that the interferer can be up to 33 dB stronger than the desired signal, and we'd still be able to detect the wake-up signature. So we can show that we have this kind of filtering across the band, so we can basically reconfigure the filter. So to conclude, I'd say that MIMO and digital beamforming arrays with reconfigurable frequency spatial code filtering are represent in the next paradigm for multiple element integrated arrays. So we want to provide some analog filtering, some digital filtering, and make that as reconfigurable as possible. There is this whole problem of building MIMO arrays at millimeter wave related to antennas and interfaces and wafer scale packaging. These are all problems also that we are trying to solve, just haven't covered it in this talk. Finally, I'd also say that given the hardware capabilities that now exist to provide reconfigurable filtering, there is a lot of opportunity for optimization and collaboration to figure out where interferers are, what are the best configuration to reject them, how to balance sensitivity versus interferer rejection in a receiver. So these kind of algorithms and approaches to provide system level interferer rejection. These are collaborations that we are working on now. So thank you for your attention. And I'd also like to thank the sponsors that have supported this work. Thank you.
All right. Well, everybody's clapping, I'm sure. That was a great talk. Thanks a lot. So we have some time for questions here. If you have a question, you can just unmute and ask it yourself. You can type it into chat if you're shy. Whatever, the floor is open.
I have a question. Yes, I'm speaking. First of all, thanks for the great presentation. My question would be about basically the last part about the ultra low power receiver for IoT application that you just showed. As you know, one of the basic requirement for this type of wireless sensor network is to minimize the cost. As I saw, yeah, for instance here, as we look at here for the, I guess for the input matching, you are using the hybrid coupler, which effectively it can increase the board complexity. And if you assume it for a, let's say, large volume to be used in industry or all the way for wireless sensor network, therefore the effective cost would be way higher. How do you want to justify this thing? Could you please comment on this?
Sure. So the hybrid coupler that we used is, I mean, it's a fairly commercially available coupler. I don't know about its cost in volume, but I will also say that this could be implemented using inductors or onboard transmission lines that we didn't because of time considerations. But a lot of these coupler approaches are fairly well known. So in higher frequencies at 28 gig and beyond, where we've used similar schemes, we've actually been able to integrate the couplers. At lower frequencies, I believe these couplers will have to be either on PCB with some performance hit, or in what are basically interconnect layers. So people are building these equivalent of CMOS active fabrication wafers. We're building wafer scale passive devices which just comprise interconnect layers or metallization layers to realize such devices. So I think those kind of technologies will enable the cost of these to be very compatible with IoT type costs. I mean, the apples to apples comparison would be that if I wanted to build a high Q filter up front, I would have to get an electrode inductor, for example. I have to get a high Q inductor. So there isn't a particular, how should I put it? It isn't that this adds to a cost of a system that already existed.
Okay, thank you very much.
All right.
I have a question. Arun,
Sure.
This is Seifi. How are you?
Hey, Seifi, how are you doing?
Good, good. Excellent presentation. Quick one. On the spatial filtering on the beams, do you have to know the direction of the noise coming from in order to cancel that properly?
So we, yes, short answer, yes. Our work is focused on, being able to provide a certain resolution of phase and amplitude weights in order to form the beam, right? I don't have that plot in this presentation, but basically we have the equivalent of I'd say 5-bit phase shifter, something of that order in our phase resolution. The detection of interferers and forming the closed loop system that nulls it, that's something that we are working on. I think that is actually a very nice collaboration opportunity with people that work on interferer mitigation at the system level.
Yeah, thank you. Yeah, they do the same thing, similar thing in the audio array processing, but they do have to have a source localization to know where the source of the noise is in order to form the beam correctly to cancel it.
Yeah, I mean, in some thoughts, I give the analogy of this being similar to echo cancellation or noise cancellation in headphones. I mean, this is, similar to that approach.
Yeah.
Actually, since you bring up audio, this is Mark Reed. I actually have a capstone project for sound localization. Is there a person I should send my team to catch up on the latest techniques? Your switch capacitor system seems real interesting.
Yeah, sure. I'd be happy to talk to them. We worked at much higher than audio frequencies. We're working at RF, but some of these techniques in arrays, for example, people have been working on sonar and ultrasound arrays for a very long time. So a lot of these techniques actually map one-to-one.
Great, thank you.
Yeah, so Soham.
Hello, sir.
Here we go. Yeah, go ahead, Soham.
Yeah. Hello, sir. Thank you for the excellent presentation. I have the following doubts actually. I saw that there are many switches implemented and that too at millimeter wave frequencies. So how did you take care of the insertion losses due to these switches? And the second is how did you handle the phase noise? Because it may affect your constellation diagram badly.
Sure. Yeah. So just to clarify, we do have some work using end-path switches at millimeter wave, which actually, will be at ISSCC in 2021. But the problem that we were trying to address in terms of spatial filtering in this work, at the 28 gigahertz didn't involve using end-path switches. The end-path switch work was at 1.4 gigahertz, and what you're saying is exactly right, which is that the speed of these switches, or more accurately, I would say the power consumption that one is willing to burn in order to drive these switches limits frequency. And these papers were, or these projects were done in 65 nanometer CMOS, which is very nice technology, but isn't state of the art. So we have seen some work by other groups that are addressing this challenge of trying to do switches at millimeter wave, both by going to other technologies or by using techniques like subharmonic switching. Basically, one switches at 1/3 or 1/5 the frequency, right? And these end-path filters have a frequency domain repetition in their transfer function. So you can leverage that, right? So that's one approach that we have seen taken. On the phase noise front, again, it's a good question. And I would say, for example, there's one of these waveforms which just shows classic phase noise limitations, right? But these are, these are design issues which can be overcome. There isn't anything fundamental in this particular implementation, for example, that cannot be fixed with buffer design, for example. So I would say that the challenge of end-path operation at higher frequencies is more along the lines of switch performance right now, or insertion losses that you would get rather than phase noise.
Okay, thank you so much.
So do we have any other questions?
Hello, I have one.
Can I ask a question?
Sure. Sorry, I'll just mute myself. And,
Go ahead.
So my name is Matthew Baroni. I'm from University of Waterloo in Canada. I'm relatively new to the end-path filter concept. Actually, thank you for having this delicate presentation. I learned a lot. So my question is, what's the main competitive technology or approach to this empath filter when we want to, for example, have these band selects and doing these frequency sweeps? And what is the main trade-offs? What are the main pros and cons of empath to them? Thank you.
All right, that's a pretty long, it's a good question. It's a long question, right? In terms of trade-offs, for example. What would be the alternative to NPath filtering? So people are trying to build tunable filters using traditional technologies like SAW and BOSS. So there is an effort to build tunable filters in the front end, right? So that's one approach. The other approach is to say that we will not try to build very wide-scale reconfigurable filters. Instead, we will parallelize by building band select filters and then placing receivers behind them. So we will divide the frequency domain into multiple bands, for example, and then use traditional filtering inside each of those bands. So that's the alternative. There are certain techniques like doing current mode receivers for high linearity, things of that nature, which are just about designing more linear receivers. So there is that axis as well, right? So try to improve the linearity of the receiver, separate the bands into multiple bands, put multiple receivers behind them. And the other alternative is to try to build tunable, for example, tunable LC filters or tunable SAW and BOSS filters for addressing these issues. In terms of trade-offs of NPath filter, one way that you can think about it is that when you generate multiple pulses, if I generate an n phase pulse, I'm effectively operating at n times the clock frequency. So I have to generate a higher frequency clock, and then I have to deal with all these issues of overlap. Very often I have to burn power in order to overcome rise time issues. And finally, the filtering provided by NPath is not that high. So a traditional bandpass filter just keeps going down, let's say, but an NPath filter would, if you go through the math, you'll find that it has a floor. So it doesn't, so even as you go further and further away from the center frequency, it isn't true that you're getting more and more rejection. So that can prove a limitation of NPath filters. I mean, that was a very quick hit, but happy to go offline and discuss.
Thank you, sir.
Thanks.